first?
Yes, you may.
Great. So for 7.16, C is asking about like a confidence interval. How
Yes.
would we do that in this context?
You do it the same way you did it before. It's asking you to do the confidence interval just like you would before. Like we did confidence intervals back in the previous chapter.
Okay.
It's asking you to, basically the question's asking you to make a confidence interval like we did, and see if you come up with the same conclusion from confidence interval that you would from the hypothesis test.
So can we use like the y over n?
Mhm.
Okay.
Yep.
Oh, okay.
Yeah, that's what it's asking you to do. Yeah.
And then for 7.110,
Mhm.
it's asking to define a critical region with an alpha of like 0.01.
Yep.
How do we do that? What's the critical region? Or like how do we find critical region?
Yep. So what we're doing with the critical region is. So when you're looking at the critical region with your alpha, so again we're treating this like we've got a normal distribution, right? So if I want this to be PR greater, right? Increase, yep, so we want to be greater. So this would be your alpha, so we want this to be 0.01, that probability. So you need a z-score here that corresponds to 1% of your distribution being above that particular point. So can you figure out what that z-score has to be?
Would you do that by using the 0.01? Or would you divide that by 2?
You would use the 0.01 because we're just doing a one-tailed test here. So we want all of the probability up in the upper tail. Since it wants to know, did the proportion of people wearing their seatbelts increase? So we know we want the P to be bigger than the original. So that's why I know to put it all above. If it just said that did the proportion change, then we wouldn't know if it went above or below, so we'd have to divide it in half.
Okay. So it's like the alpha, like the significance level,
Yep.
is that like basically like confidence interval?
Yeah.
So that's why we can do that.
Yeah, it's the same kind of idea. Yep. So you can either get this off of your table or off of Excel, either or.
And then what do you do once you find the z-score? Is that like your critical?
That's the critical region is then any z-score that lands above that. So then your critical region would be
Like whatever z is
yeah,
to 1
to infinity.
to infinity.
Yeah, because you're going to calculate it as a z-score in this case, because your z will be your p hat minus p over square root of p times 1 minus p over n.
Yeah.
That's how you would do it. So your critical region is going to be defined in terms of your z here.
So, follow-up question. So, like, your critical region would be that area that's greater than.
Yep.
So you're like wanting it to fall on the left.
You want it to fall on the right.
Or I mean, like, because isn't like the critical region bad if you don't want it?
If you're looking to reject the null hypothesis, then you do want to end up in there. And in this case, they conducted the campaign to get seatbelt use to be higher. So you would hopefully reject is where you want to be. Is okay? Maybe? Well, let's look at another example or two here to make sure that we're all on the same page with this. So, let's see, which one do I want to do? Let's look at 7.1-11 here. It says the management of the Tigers baseball team decided to sell only low alcohol beer in their ballpark to help combat rowdy fan conduct. They claim that more than 40% of the fans would approve of this decision, So they set up a hypothesis test where the proportion was 40% versus the proportion is greater than 40%. Part A asks you to find a critical region with alpha equal to 0.05. So the first thing we need to ask when we're finding critical regions is, are we talking about a one-tailed test or are we talking about a two-tailed test? One. In this case, it's one, because we're just going one direction, right? We want the probability to be greater than 0.4. So since we're looking at a one-tailed test, if we're thinking about the picture, we want this probability to be 0.05. All of it's going to be in one tail. I know it's in the right tail because it says probability is greater than 0.4. So we want the z-value associated with 0.05. And again, we can find that using the table or using Excel. I'll use the table for the time being because I want to use Excel for something else here in a second when we get to the end of this problem. But if you look at z sub 0.05, you should find 1.64. I can get there. On the wrong page. 1.645. It's like 1.6449 something if you use it in Excel. There's a nice little table at the bottom of page 584 that gives you the z sub alphas for various alphas. Right at the bottom, you can look right at the bottom of the page. It even has z sub alpha listed for you, and then the alphas across the top. Yeah, makes it a little bit easier. So when we're doing the critical region here, we're going to reject the null hypothesis if our z that we calculate will be greater than 1.645. Notice that had nothing to do with the only thing that we used here that had anything to do with the setup of the problem is the fact that we were doing a right tail. The only thing that had anything to setting up this critical region, that's the only thing that we used to set up the critical region. It's the only thing we used it for.
So then how would a problem be phrased if we use two tails?
It'll say different from, or the proportion has changed. Okay. That kind of thing. Okay. Yep. Increase would be a right tail, decrease would be a left tail. If this were the proportion was less than 0.4, then we would reject if z was less than negative 1.645. It would be on the left side. So we'd have to flip it over to the other side. All right. So now we can actually calculate our z-score if I give you the information that they have in the problem. They did a random sample of fans. In fact, they said they randomly sampled 1,278 fans. 550 approve of the decision. So when we do this then, we calculate our z. We'll have 550 over 1278 minus your p, which is 0.4. And then we'll have 0.4 times 0.6 over 1278 on bottom. Remember, when you calculate your standard deviation for these, remember we're assuming that the null hypothesis is true and trying to see if there's evidence to refute it based on the sample. So when we calculate the standard deviation, we're using the null hypothesis. The null hypothesis is purported value for p. Easy for me to say. Yes. Well, do I have trouble? I always have trouble. In that case, it was just the word I was having trouble with. But generally, I have problems. Lots of them.
I got 2.
More than 99 of them.
I got 2.215.
Did you get
2.215.
2.215? Oh, that's a bad joke, I know.
So bad it's funny.
Oh, well, that was the point. I was hoping it would be funny.
I didn't laugh.
What's that?
I didn't laugh.
You didn't
Nobody
laugh?
asked you.
Nobody asked you. That's true. Chelsea's exactly right. Nobody asked you.
I got 2.21.
Excellent. Yeah.
Yeah.
Yeah. Cool. All right. So, what'd you reject? Good.
Yeah.
Go ahead, Sam. Go ahead. No, go. So what are we supposed to conclude from this? Are we supposed to conclude that low alcohol beer does not make fans less rowdy, or?
No, the setup of the problem was the Tigers said that more than 40% would approve of the decision. So we would conclude that there is evidence that more than 40% conclude, approve the decision. I'm not as worried about the interpretation statement.
Okay, good. I was going to ask if you were cared about that.
No, I'll let Dr. Lee teach you that part.
Okay. Dr. Lee really cares about that.
Yep, and I really don't.
Like, well, no, there are people's heads in the way. Yeah.
Yes, Steve.
Why do they say fail?
Because you're not really accepting it, you just don't have enough evidence to reject it. So that's why you fail to reject it.
That was just rude.
Here,
So if it's less than 1.645, then we would.
you say fail to reject or do not reject, yeah. Yep. And then you can always put it in context. So the context is always the same. Either there is evidence to reject the null hypothesis, or there is not evidence to reject the null hypothesis at whatever level. Which is why I don't really care, because it's always the same conclusion, it's just different contexts. Do you have a question, Morgan?
Yeah, so how do you, are they always the standard normal? Like, because we've done some with like the binomial. Like, how do
Since the samples are so large, we're going to use the normal approximation.
Oh.
You could use the binomial if you really, really wanted to. Because if you tried to use the binomial for a sample size of 1,278, you'd have to play around with how many successes you would have to get to this point. And that would require more computational, well, my guess is you could probably play around with Excel enough to get it. It's just more effort to do than with the normal. Yeah, Sam?
So when you want to prove they're different, why do you need the alpha themselves? Because if, like, for this one, if your alpha is 0.025, then it's 1.96, so it's bigger anyway. So why do you need a smaller alpha? Definitively bigger. Versus if you had a bigger alpha or a smaller alpha to compare it for the different test, why do you need such a bigger alpha?
Ask that again? I'm not sure what you're asking me. Sorry.
When you're doing difference tests, right? You divide your alpha in half.
Yes,
So you
because the sample could be above or it could be below. That's why I have to divide my probability in half. That's why we do it in half. Which will make your z's bigger, yes. Right. But part of the reason for that is because if they really are the same, you would expect half of the time one of your samples is going to be bigger than the other, and the other half of the time it'll be the other way around. So that way you don't want to have it just random chance to say I'm above a certain point. That's why you pour it out a little bit more.
Well, let's say for this one, z-score is 1.8. It's in between 0.05 and 0.025, right? It's in between alpha and alpha over 2. So how come you can say it's definitively greater than, but it's not definitively different than?
Because if they were looking at greater than, we would expect that all of the samples for the one of them should be always bigger than the other. If we're doing a difference, then again, like I said, if we assume the null hypothesis is true, we wouldn't expect one of them to always be bigger than the other. We would expect it to be flipped. So if there really is a difference, then we're going to expect that one of them has to be definitively bigger than the other, which means we need it farther away. That's the best answer I can really give as far as that goes.
That's why I want to work backwards and calculate for what you're given, and then see what that corresponds to.
Oh, you can do that too.
With that,
That gives you, that will tell you how you would reject at a particular confidence level. So that's actually what I was going to mention here. Let me go over to Excel. So we had, I guess I need a keyboard. We had, there it is. 550 and 1278, were those the two numbers?
Yeah.
All right. So there's our P. So our Z-score was that minus 0.4. And then if I could actually type today, that would be helpful. Square root of 0.4 times 0.6 over the 1278. What was our Z? All right, so let me do this. Okay, so this 2.215 gives us, it fell into our rejection region so that we know that we reject at the 0.05 level, the significance level, the 0.05 level. But actually it's a little bit better than that because it was bigger than the 1.96, right? So there's another value associated with this Z-score that we got that tells us a little bit about the significance level as well. Oops, why don't I just use the value? A5. Oops. Oh, that's not what I wanted. I want this. All right, so I want this, and then I want cumulative, and actually, I want to do 1 minus that. Sorry. I have struggle bus today. All right. So what I just computed there was we got that Z-score. We had the Z-score of the 2.215. That 0.013 and change is the probability that we're above that Z-score. Right? The Z-score to the right, that's why I did the 1 minus, to get the probability that we're above that. So if this were your cutoff here, this would be your significance level in that case. It's the probability that you have, if you took another sample, if the null hypothesis were true, it's the probability that any other sample would be at that value or higher, if the null hypothesis were true. So you really could reject at this level, given this particular sample, which is better than 0.05, right? We refer to this as the p-value, and you can actually do hypothesis testing relative to that p-value. So going back to Sam's question, if you had something that was between the 1.645 and the 1.96, you would reject it at the 0.05 level, but not the 0.025 level. So your p-value would be in between the two. Okay. So you can base it off of the p-value, which is what you were just asking. So you could do it that way. The lower the p-values, the more the significant the result. The significance levels go down. The significance level goes down, so the result's more significant if the p-value is even lower. That's the idea behind it. So you can do rejection or not rejection based on the p-value and based on your significance level. You'll see different things in actual research and literature that will just declare what the p-value is, or whether or not they would, and then do the significance level at that point. So a lot of the social science papers, the p-values of about 0.1 are pretty good in the social sciences when you're doing hypothesis testing. For more scientific testing, you'd probably want your p-values lower, especially if you're making decisions that are going to cost millions of dollars. You want to make more certain than 10% of the time you're wrong. Right? If the decision is going to cost $10 million, if you're wrong 10% of the time, you're going to lose $1 million. That could be expected over time. So that wouldn't be very good. Yeah, you probably wouldn't have a job very long.
But in the social sciences, it's okay.
In the social sciences, it's okay. Because there's too many, I mean, in the social sciences, there's a lot more variance in what's going on based on just, well, human interaction, for one. Yes?
So is that 0.013, is that like the new alpha?
That would be the lowest alpha at which you would reject based on this sample. And actually, it would be the lowest alpha that you could ever reject at because you found a sample that had that value as its probability to be greater than. So you could never have another alpha that's even smaller. Yes.
Is the alpha defined as a limit?
You could define it as a limit, I suppose, but you'd have to have some way to get a handle on what the samples would look like every time you took it. So, while I think you could theoretically define it as a limit, I don't think practically you could define it as a limit. Because you would have, I mean, at that point you'd have to know what the distribution was to figure out what the limiting value would be. But I do know that I could never have an alpha value smaller than this based on this one sample. The alpha value could only go up from here, not down. Because I've already found a sample that has that p-value. So I would know that I couldn't possibly be any... I could not lower the significance level anymore based on that sample size. And I could use a different sample size maybe and be able to do it. But based on that sample size, I already have a sample that gives me that p-value, so the significance can't go down anymore. The significance level can't go down anymore. You okay with that? Okay. Okay. So, if you were doing this for, and the whole point of the rest of this section, the rest of this chapter actually, is how do you get different, well, this z-score here is we typically refer to as a test statistic. We're calculating a hypothesis test, so this is your test statistic.
There. Yeah. You're right.
What?
That's Dr. Lee's song.
Okay.
Also, Dr. Joe, you know why you do that?
Fine, it says so.
What? Because what then?
The reason, if I asked you why something was true, you would drive it for me. If I ask her why, or if anybody asks her why, she goes, because formula says so.
Okay.
Formula sheet says.
The formula sheet says so.
It's like we're playing Simon Says.
All right. So, say you were doing a difference. The rest of this stuff out of this chapter really is just trying to figure out how you calculate the test statistic and what distribution you use to check whether or not you're going to reject. Okay? So, in this particular section, I also talk about differences of proportions. So, if you had a difference of proportion, what would your test statistic look like? If you had a P1 and a P2. So if your null hypothesis were P1 minus P2 is 0, and say your alternative hypothesis was P1 minus P2 is greater than 0.
One-tailed test.
Okay, so that would be a one-tailed test, right? But what would you use for your test statistic then?
Represent the ones we did like in the past, like
Hmm?
second degree or third, you have like the P1 times 1 minus P1.
Mm-hmm.
P2.
Right. So when we did the one parameter, the one population proportion here, this was our sample proportion, right? This was our given proportion, right? And this is our standard deviation. But now we're doing differences, right? So what would go on top? Okay, the difference of the P1 hat and the P2 hat would go on top, because that would be your test when you're doing your statistic. Then that would be your point estimator for the statistic, right? The P1 hat minus P2 hat. What would go here?
Minus P1.
There's like it's like D0.
Oh, yeah.
So
The difference between
the difference in this case, we're assuming it's 0, right?
minus 0.
Okay. And then what's this going to get replaced with? And I think Morgan was alluding to that a minute ago.
Yeah. P1 times 1 minus P1.
Yep. Right. Yep. So your Z would be P1 hat minus P2 hat. And then if there really was a difference, if the difference was purported to be a certain value, you could also subtract that off. But in this case, we're assuming that the difference is 0. And then you would have the square root of P1 hat times 1 minus P1 hat over N1 and P2 hat, 1 minus P2 hat over N2. Now, one of the reasons, besides the fact that I just wanted to mention how we would derive this particular test statistic, I want to compare this to the previous. You have a question, Sam?
Is that adding or subtracting?
That's adding. Now remember the previous one, we wrote, just to compare it below it, we wrote this. Right? Now notice something different's going on in the denominators. Did I use the point estimator or did I use the actual, what I thought was the population parameter in the denominator here? Did I use the point, what it was, right? We used what we purported it was in the null hypothesis, correct? Right? This is the P, not the test statistic, P hat. Up here, we had to use the P hats. Why? Why are the P hats being used in the top one rather than P? I knew you were going to say that. Well, I was looking at you. I was waiting for you to say it. No, we don't have it, right? They didn't give us P1 and P2. They only said that we're purporting that they're the same. We're not given the P1 and P2. So the best we can do is estimate the variances based on the point estimator. See, the best we can do. Right? In the one population parameter, the one population proportion, we're purporting that the value is a certain value. So we're assuming that value is true when we use it. Right? But in the second one, the only purporting that we're doing is that the population parameters are the same. Right? So we're using the P1 hat and the P2 hat to use the variances. And we're doing this because we're adding the variances, right? And we're assuming that on the underlying distributions, the variances would be equal. So this is what's giving us our estimate for the overall variance. So that's why we have to use the P1 and P2 hat here versus the P here. Okay, so there really is a difference between the two what we're using. Yes, Megan.
So for the general formula, you said, like, for this one, since it's minus 0, then nothing goes on the top, but what if it wasn't 0?
Then you would just put the value. Like we have here, you would just...
the value.
What if this were, say, D, then you would just put minus D here.
Okay, so is it the value that each?
Yeah.
The null
Yeah. Is this okay?
Yes.
Okay. Yes, Michael.
On our formula sheet, it says for the, oh, it's small.
What's
Yeah,
wrong?
Never mind, we're good. I'm good.
Is this still 7.1?
Yes,
Yes.
sorry.
Yeah, Morgan.
So, like, the first one we had to be because that is what we that's what was based on our data, like, we had. But, like, this one, like, why wouldn't we have the piece that we're starting with?
We're looking, say we were looking at whether or not there was a difference in the approval ratings for Democrats and Republicans of what the job the president is doing. Well, we wouldn't necessarily know what the approval rating was specifically for the Democrats and specifically for the Republicans. To start with, we would just want to know, is there a difference between the two? Would we say one group is definitely less approving than the other? So we wouldn't necessarily know what they were ahead of time.
Okay, so like the first one, we were starting with one, but now we kind of have two different things.
Right. Say in the past when certain things happened, 25% of the population approve of what Congress is doing. Now that something else has changed, is the approval gone up or down? That'd be the idea. Versus if you've got two different groups of people and you're trying to see whether or not they have the same or different approval ratings, then you would use something like this. Yeah. Sam, did you have a question? I thought I saw your.
I figured it out.
Okay.
Maybe I'll ask anyway.
Okay.
Would there ever be a case where if you were to define one variable in terms of the other, like let's say you're doing Republicans versus Democrats, right? Or if you switch it up and do Democrats, which only when your conclusions all would be the same.
It would be all the same because it was just flip the tail, which tail you were looking at. Yeah. Yeah. All right. So, going on to doing other tests for other types of statistics, section 7.2 talks about, that was a nice gasp.
That kind of scared me, not gonna lie. I
Thank
thought
God
there
you're
was
not-
something
thank God
actually
you're not
wrong.
lying to us.
What's wrong?
I thought there was actually something wrong when you gasped there.
Yeah.
Got me actually worried.
All right, so when we do section 7.2, they start talking about doing tests about one mean. It's the same idea. It's just going to be we're going to try to determine if the mean value is a certain value. Is it above a certain value? Is it below? Is it different from? It's the same kind of concepts. So again, to motivate this with a specific example, let's say we look at,
Michael.
see, do they have one where I don't have to type in a bunch of data? Yeah, let's look at 7.2-5. All right, so 7.2-5 here says they've given you a mean birth weight in the United States and the standard deviation. So they tell us that in the U.S., the mean birth weight in grams is 3315, and the standard deviation is 575. They want to test whether the mean birth weight in Jerusalem is less than what the mean birth weight is in the U.S. Okay. So your null hypothesis versus your alternative hypothesis. Okay, so they want to know, is the mean birth weight in Jerusalem less than the mean birth weight in the U.S.? And we know what the mean birth weight in the U.S. is. So what's your null hypothesis going to be? Right? And if we want to test whether or not it's less than that, what's your alternative hypothesis going to be? I got a little excited. Good writing threes.
All threes.
All right, so again, this is for mean in Jerusalem versus the mean in the U.S. So I probably should have a different subscript on these two things. So I'll put a little sub J here on this mean just to emphasize that it's different. Make a what?
Make a sailboat.
Make a sailboat?
Yeah, make a sailboat for MJ. Instead of having a change when it's so
It's like these things.
I don't know what that
You can't
means.
just do like a normal.
You mean
We always, I don't know, what do we always do? Make a sailboat.
Smiley face.
I do that too, but I didn't know what he was talking about. I thought there was some reason I was supposed to turn that into a sailboat.
But it's
I'm
always
just
a
saying, we
sailboat.
can't have this, like, you can't have mean and mean.
So yeah, I could do it like something like this. I don't know. Try to make a sailboat out of it. You said make a sailboat. I tried to make a sailboat. All right. We're doing this with means now rather than proportions. So if I want to develop a test statistic of whether or not whatever I got from my sample should deviate from what we think the mean is enough, what do you think we should probably use for our sample statistic, our test statistic here? we should probably use difference of a couple of things, right? So we've got a purported mean, right? Now, I didn't tell you what the sample mean is, but we probably should use the difference between our sample mean and our purported mean, right? And then we need to divide by something, because what do we know about the distribution of sample means? If the underlying population is normal, or if the sample size is big enough, what do we know about the distribution of the sample means? It's normal, right? With a mean that's the same as the mean of the population. And what's its standard deviation?
5 by square root.
Yeah, okay, so it would be sigma over square root of n, right?
Oh my.
Can you stop dropping things over there? Huh? Sorry.
Right? So all this is doing is standardizing the distribution, correct? It's just making it a standard normal?
Yeah.
Isn't that what we just did with the population proportion?
Yeah.
Literally the exact same thing that we did with the population proportions, right? There's nothing different here. So if you're defining critical regions, we're going to define it in the exact same way for this one. So in this case, it wants us to test at alpha 0.05. So if we do an alpha is 0.05, we're looking less than, so we're over here, correct? We want this area to be 0.05. So we'll find our z sub 0.05, either using Excel or using the table. And in this case, it'll be negative because we're below the mean. And our rejection region will reject H0 if our z statistic here is less than negative 1.645. So notice it looks a lot like what we just did in the previous section, doesn't it?
It does.
Yeah, okay. In the previous section, we used the fact that if n was big enough, we could use the normal distribution to approximate the binomial, and then converted it to a standard normal. Same idea. Here's exactly what we're doing here, right? Subtract the mean, divide by the standard deviation. That gives us normal on 0, 1. So we've got a test statistic now that we can do, and we'll reject based on our rejection region for the normal distribution, just like we did in the previous section. Yeah, Sam.
But we have two unknowns. How do we check?
What do you mean we have two unknowns?
We don't know what that is.
I haven't told you what the sample is yet. I was just trying to set up what the test statistic was. All right, so in this problem, they tell you that the sample from Jerusalem your mean was 3189. The standard deviation of the sample is 488, and the n is 30. And just to remind, our mu was given to us as 3315, and our sigma was given to us as 575. All right. So based on the sample, we want to tell whether or not we reject. All right. So what are we going to use for x bar? The 3189, right? That's the sample size we're given. What are we going to use for mu sub j? 3315, because that's what we're saying the null hypothesis is, right? Remember, when we do hypothesis testing, we're always assuming that the null hypothesis is true. Okay, so we use the 3315 for the mu sub j. In the denominator, what are we going to use for sigma?
575.
Yeah, 575. We're actually given the sigma for this one, right? Remember, we're assuming the null hypothesis is true. In this problem, I didn't write it all down, but in the problem, they're assuming that since the mean birth weight in the United States is mu sigma squared, they're assuming that the one that's to start with, that the one in Jerusalem is the same, has the same distribution. So we would use the 575 and not the 488. Okay? We're actually given the extra information of what we think the variance is for the distribution to start with. If we weren't given the sigma, what would we use?
48.
You just spit on yourself?
I had a movie.
So yeah, the answer to that question is yes. Okay. Just double checking, yeah. All right. So we were going to use the 575 instead of the 488 in this case for the sigma.
So they just gave us
To make sure that
make sure we knew.
Yeah, that's right. Yeah. Now, in most cases, you're not going to be given it the sigma, so you'll use the S.
Okay.
But in this case, yeah, they were just kind of testing the concept. Yeah.
So, like, why wouldn't we like need to find the sigma?
Say that again.
Like, why wouldn't we need to find the sigma if we weren't given?
You would use the what from the sample. You would assume that was the same. Use it as the point estimator. So you would use S if you weren't given sigma. But since we're given sigma, we'll use sigma.
Got negative 1.2.
So you got Z was equal to negative 1.2. Is that what you said?
Yeah.
Maybe.
Yes.
So we had 3189, 3315, 575 over the square root of 30 was negative 1.2.
Yes,
Okay.
sir.
And some change. Anybody put in 488 and see what you get? Just
I
out of
got
cu-
you, Dr.
just, yeah, out of curiosity.
It was negative 1.414.
Okay, so you would have rejected either way. Okay, I was just wondering if they made it so it would have a different number where you would reject with one and not the other.
That would have been really smart.
I would have written it that way. All right.
Not smart.
So anyway, this tells us what about the conclusion?
That you do not reject.
Good.
Don't support each other.
With insufficient evidence.
Correct.
We can tolerate it. It's a tolerable number.
Okay, it's a tolerable number. And then we could also calculate a p-value associated with this by doing the same kind of thing we just did on Excel. So we want to do this on Excel. If I go over
Normal distribution.
norm.s.dist. Yep.
Then did.
Then diddly did.
Yeah.
All right, so I'm going to do the norm.dist because I'm going to be lazy. So the value was 30. I don't want to have to type in all the other things. 3189 was the value we had. The mean we were using was 3115. The standard deviation was, thank you. Thank you. There's your p-value.
That's good enough for 12 times.
Probably not even for them.
I would hope not. That is.
So that's your p-value. I didn't have to do 1 minus in this case because it was on the left side. I had to do 1 minus before because it was on the right. So I didn't need to do the 1 minus here. So it was just norm.dist. And since I didn't actually have the values computed in Excel, I just used the regular old norm.dist where I could type in the value and the mean rather than just putting it in the standard normal.
So, what's the p-value again? What does that tell us?
It's the probability that any other sample would be less than what you got, or would be I'll say at least as good as what you got, because you want to have it go. It's either that value or below in this case. This is another way to look at significance.
Okay.
So treating your sample as worst case scenario. What's the probability that your sample was worst case scenario?
So that's why it's at least that.
Yeah.
We still have 2 minutes.
You're saying that that's the p-value, anything less than the 4.
So
is
that-
what,
So this is the probability that any other sample that was generated would be have a z-score of negative 1.2 or below. Yeah, that's what it is. It's kind of like think of your sample as worst case scenario.
Okay.
If your sample was worst case scenario, what would be the probability associated with it? So it's that value or below in this case because we were looking below. All right, we'll do more of these next time. We'll do ones for small sample means, and we'll use t-scores. We'll do differences of means next time as well.
So will we be able to do any of the 7.2?
If you can, yeah, you should be able to. Yep.
Do we have class on Friday?
No. I already told you that.